Welcome to the video on Laplace transforms. In this video we'll learn what Laplace transforms are, some of their useful properties, and how to use them to solve ordinary differential equations. So, the Laplace transform definition is right here. So we have a function, f of t, it's a function of time, and we put that into this integral, so we multiply by this function here, e to the minus st. Okay, and then we integrate with respect to time, dt. Okay, so after the integration, this variable s will stay, this variable t will be gone. Okay, now s is a complex variable, that's why we had the review of complex numbers. So s can be represented by s equals sigma plus j times omega. And f of t is a continuous function of time that is 0 anytime before t is equal to 0. That's why we can have this this function like this. So the Laplace transform converts this function in time to a function of a complex variable s. That's what it is mathematically. Now to undo that, the definition is like this. Okay, so if you want to get back the original function of time, you take the Laplace function f, which is now a function of s, okay, you put it in a different looking integral, okay, and you now integrate that, okay, and that will basically return you. We won't actually evaluate these integrals, but this is how the Laplace transform is mathematically defined. So we have two representations of a signal. Okay, we have the one that we're familiar with, the time domain representation, and now because of this Laplace transform, we're going to have a second representation, which we're going to call the S domain. Signals and systems will have both a time domain and an S domain representation. The Laplace transform has some very important properties that we will use, which will help us in solving differential equations. Alright, so given that we have two functions of time, f1 of t and f2 of t, and that their Laplace transforms are cap f1 and cap f2, alright, and a and b are arbitrary constants, then this equation holds. So if I take the Laplace transform of some combination of these functions of time, a f1 plus b f2, then the result will be like this. A times the Laplace transform of f plus b times the Laplace transform of f2. So that's linearity, just like just like we defined. That's the superposition principle. Okay, now very important. Note that if I take the Laplace transform of f1 times f2, I do not get f1 capital F1 times capital F2. Okay, this does not hold. So keep that in mind. Okay. This holds. This is linearity. This is not true. Okay. Alright, so question. If I have u equals to u1 of t and 4 times u2 of t, what is the Laplace transform of u of t? Okay, and here's the answer. Alright, this seems simple because maybe we know what these are, but so I can take the Laplace transform of this function of time, and get capital U1 of S, okay, plus I just bring this 4 in, okay, and I get capital U2 of S, okay. I can just do this. Another one consequence of this is that I can do these by terms, okay. I don't have to do the addition first. I can do the addition later. Okay. Differentiation is also very easy with the Laplace transforms. So again, here we have f of t as the time domain function, and we'll represent the answer, the Laplace transform of f of t, as capital F of s. Alright, so the Laplace transform of the derivative of f of t, here, df dt, is basically like this. It looks like this. So the derivative, if you have the derivative of f of t, you just say s times f of s, okay, which was the Laplace transform of the original function. So the Laplace transform of its derivative is just s multiplied times the function. That's very easy. But we also need to subtract off f at 0. Okay, so this is the time domain function evaluated at 0. All right. So you can actually keep this going. You can chain this thing, okay, and you wind up getting s squared s f of 0 minus f dot 0 if you take the double derivative and you take the Laplace transform. If you take the triple, you can see this actually just keeps going. Okay, so we have s squared, and s cubed for the first, second, and third derivatives. Now, whenever we have 0 initial conditions, we can go right back and forth between third derivative and s cubed times Laplace transform of f of s. Okay, but don't forget that if initial conditions are important, we are going to need to include them. Okay. Integration is very easy with a Laplace transform, similar to differentiation. Okay, so if I have the integral of f of time, okay, like this, and I take the Laplace transform of that, all right, the result is f over s. Okay, so the conclusion to that is that if I want to integrate the signal, I just divide by a power of s. That's all. Very, very easy. Okay, so let's do a Laplace transform. Okay, so we have a unit step function. Okay, so at time t equals 0, this goes from 0 to 1. Okay, so it's a constant 1 after that. And we have the function f of t equals sine of 2t. Now if I tell you that the Laplace transforms for these two functions are as follows here. So u of s, you take this constant 1, you get 1 over s. That's the Laplace transform of 1. Okay, and also this function, sine of 2t, the Laplace transform of that function, somebody went through and actually solved out the integral, okay, and you get this function, 2 over s squared plus 4. How can we use these properties and the knowledge of just these two functions to find the Laplace transform of this function, e of t equals 2 plus 3t plus 5t squared plus 4 cosine of 2t? Because none of these terms are exactly equal to either of these functions. Well, we'll break it up into terms. This is equal to 2 times u of t, the first term. Okay, you can see that. The next term is 3 times the integral of u of t. Okay, this term is actually equal to 5 times 2t. Okay, which you notice we have 3t here, so this is 5. This is 2t, and the integral of that. Okay. And then finally, we have, here's 4 times cosine of 2t. Well, 4 times cosine of 2t is related to sine of 2t, okay? It's actually 2 times the derivative of sine of 2t with respect to time, okay? So if we write it this way, we can try to exploit what we know already about this one and this one, okay? So if the Laplace transform of 1 is 1 over s, then the Laplace transform of 2 will be 2 over s. If this is 3 times integral of u of t, okay, well here's u of s, all right, so if we divide by a power of s, and then we multiply times 3, we will get the Laplace transform of this term, 3t. Okay, if we take the Laplace transform of this, okay, now again, this is basically 5 times 2t, okay? So we have a 5 times 2, and take the integral of that term. Anyway, it's going to be 10 over s cubed. All right, and last but not least, let's deal with this one, okay? So this is 2 times the derivative of this function, okay? So we have a 4 instead of a 2, and we multiplied by s. Okay, so we multiplied the entire thing 2 from here, and s for the differentiation. Okay, and we have this. Okay, so that is an example of how you can use these properties of integration, differentiation, and linearity to basically solve many, many Laplace transforms, as long as you can relate them to things that we already have. Okay, and we have many of them. Okay, so on the right side here, you'll see that we have a table of Laplace transforms. Okay, so here's that function u of t equal 1, and you see the 1 over s, and for some various other functions that you'll find useful. So we'll use this table extensively to try to take Laplace transforms, rather than actually computing the integral. All right. There's two important theorems that we'll use in this class. They are the initial value theorem and the final value theorem. They look very similar, okay? And if you want to find the initial value of some function of time just after the point when, just after the 0, so approaching 0 from the right side, you take the limit of the Laplace transform of that function, f of s, multiply times s, and then take s to infinity. Okay. Now, on the other hand, if you want to do the final value theorem, and we'll use that a lot, okay, if you want to find the value of f at infinity, so you want to see if f ever settles out, okay, you'll take the limit as t goes to infinity. Anyway, that's equal to the limit as t goes to infinity of f of t, and you take s times f of s, okay, multiply the Laplace transform by s, and then take s to 0, okay. Find the limit as s approaches 0, and you will find the value as t approaches infinity. Okay. So, given that f of s is equal to the Laplace transform of f of t, how would you find the initial slope of the response of f of t without knowing the function f of t? Okay. So, the initial slope, that's differentiation, right? We want to find the initial value of the derivative. Okay. So, in other words, we need to find the Laplace transform of the derivative of this. Oh, that's easy. If you remember, the Laplace transform of a derivative is just right here. We just need to multiply by an s, okay, for 0 initial conditions. Okay. So we can take the limit as s goes to infinity for s squared f of s. Okay. Now, an s-domain representation f of s can represent a signal, okay, like we've been talking about, as a function of time, or it can represent an operation. Most of the time, the representation can be inferred from the context, but when you're doing algebraic manipulations, one should be very careful in distinguishing the signals from the operators of the systems. Okay, so this is kind of confusing, but with practice this will become more clear. Okay, so remember that the Laplace transform of a unit step function, u of t equals 1, okay, for time t greater than 0. All right, this is the Laplace transform is 1 over s. Okay, but integration, okay, in time is equivalent to multiplying by 1 over s. Okay, so in other words, this u of t equal 1, u of s is equal to 1 over s. Okay, but also if I have an integral, I get 1 over s squared. Okay, so you're going to have things that look the same but actually represent very different things. So in this equation here, this u of s is equal to 1 over s. This thing here is also 1 over s, but it's actually the integration operation here. Okay, so you'll get familiar with this, and it will also help as we do more problems with block diagram algebra. Okay. The inverse Laplace transform. We're given some S-domain function, f of s, and we want to find the function, the time domain function, f of t. We use the inverse Laplace transform. Here's the procedure. First of all, write that function f of s as a rational function, okay, with a numerator and a denominator. And then secondly, use long division, polynomial long division, to make sure that the numerator is smaller than the denominator in terms of powers. So if you have a power of s to the fourth on the top and only s squared on the bottom, this won't work. But you can use long division to write it as two parts. Okay. Next, you'll use partial fraction expansion to break up the strictly proper rational function that you just created into a series of components. And you need to make them into components that you know the inverse Laplace transforms of. And then you can use that inverse Laplace transform table on the individual components to basically get back to the time domain. Let me illustrate the partial fraction expansion because that's difficult to understand. So first of all, we need to write, we're going to start off with a rational function here, okay? So I have some function f of s, okay? This is my Laplace transform, all right? And it's in a rational form. I have a numerator as a function of s. I have a denominator as a function of s, okay? And I need to have m less than n, okay? It is possible to write this in this form, okay? I have these coefficients a1, a2, all the way up to an, divided by s plus p1, s plus p2, okay? So these p's and these z's essentially are the solutions, the roots of the polynomials, okay? So p1 will make this denominator 0, so will p2, okay? So this works, this top approach works if you have distinct poles. So P1 is different from P2, P2 is different from all of the other ones, and Pn is different from all the previous ones. If you have multiple poles, in other words, P1 is the same, okay, we have to do it like this, okay? We still need three terms, and we get them by having an s plus p1 squared and an s plus p1 cubed on the bottom. Okay, so this is the first step. We need to break this up into different parts, okay, different terms. Now, how do we solve for these coefficients? There's a couple of methods. One is to cross multiply and get the individual components back into a single rational function and then solve n equations. And I'll show a little more what that means. There's also a formula called the method of residues, okay? Now here you can actually take this function here, multiply times s minus p1, or s minus pi, and then evaluate s at pi. So this formula actually will only work as well with the distinct poles. So, but this gives you a very easy way to figure this out. So. And there are some other methods as well, like MATLAB. Let's do an example of solving for these coefficients with partial fraction expansion. Suppose my function in the Laplace domain is f of s, and I've been able to write that as b of s divided by a of s. Okay, so I've been able to factor my numerator into s plus 6 and s minus 1, and my denominator into s plus 3, s plus 2 times s plus 1. Okay. I can rewrite that like this, as follows. Okay. I have three coefficients, a1, a2, a3. Okay. And then those are their denominators. This is how you do the partial fraction expansion. Now, I know that I can put these back together. Okay. If I multiply this a1 times s plus 2 and s plus 1, I can get it over a formula like over the denominator like this. Okay, so let me do that for each of these terms. Let me multiply by the other two. Okay, and I'll wind up with a monster denominator, or a monster numerator over the same denominator as this one. So let me multiply out this as well. and I will get s squared plus 5s minus 6. So now you see that since the denominators are equal, the numerators must also be equal. So if the numerator here is equal to the numerator here, then I have this equation that I know is true. Okay, a1, a2, and a3 have to make this equation true. So if a1 times s squared, a2 times s squared, and a3 times s squared are on this side, they have to add up to 1. Okay, so 1 equals a1 plus a2 plus a3. Okay, then look at the 5s, that power. This 5 has to be equal to a1 times 3 plus a2 times 4 plus a3 times 5. Okay, and the same thing for the constant. So here we have one equation, but we can break it by components into 3 equations. And there are 3 unknowns, therefore this problem can be solved. It's just algebra. Okay, once we know the a1, the a2, and the a3, we can now take the inverse Laplace transforms of these individual components, and we can get back to our Laplace, to our time domain solution. Okay, so what we'll have done is taken the Laplace transform of a signal in the time domain. We'll do something like this, okay, and wind up with a Laplace transform solution. And then we'll take the inverse Laplace transform to find the time response. Okay. All right, so that is all for Laplace transforms. Thank you very much for watching.